objective is to provide a basic understanding of key steps of oil and gas production and monitoring from a scientific and technological point of view. At the end of the day, we have to drill holes in the ground in order to definitely determine that there is a significant amount of oil in the desired location and to produce the discovered oil. Here's some key learning objectives. Again, the importance of porosity and permeability of reservoirs in oil and gas production, including methods of artificially stimulating permeability of reservoirs for low permeable reservoirs. The importance of fluid viscosity in oil production, methods used to artificially reduce fluid viscosity. The importance of directional drilling in modern oil production. The stimulation of oil production by water and gas injection into the reservoir, and the importance of seismic data acquisition and imaging in modern oil production. Let us start by watching these drilling videos.
Let's take a look at the horizontal drilling and stimulation processes that have made shale exploration so successful. A drill bit is mounted on the end of the drill pipe. As the bit grinds away, a mixture of water and chemicals called mud is pumped into the hole to cool the bit and flush the cuttings to the surface. The mud also cakes on the walls of the wellbore, keeping it intact. Similar to a vertical well, the hole is drilled to just under the deepest fresh water near the surface. The drill pipe and bit are then removed. Surface casing is inserted into the drilled hole to isolate the freshwater zone and also serves as a foundation for the blowout preventer, a safety device that connects the rig to the wellbore. Then, cement is pumped down the casing and out through the opening of the shoe at the bottom of the casing. It is then forced up between the casing and the hole, sealing off the wellbore from the fresh water. The cementing process prevents any further contamination of the freshwater aquifers. The pipe and bit are lowered back down the hole to drill through the plug and cement, and continue the vertical section of the well to approximately 500 feet above the planned horizontal leg. This depth is called the kickoff point, where the curve will begin so the horizontal section can be drilled. Up to this point, the process is the same as drilling a vertical well. Again, the pipe and bit are pulled out of the hole, and a downhole drilling motor with measurement while drilling instruments is lowered back into the hole to begin the angle building process. The distance to make the curve from the kickoff point to where the wellbore becomes horizontal is just under 1/4 mile. Once the curve is completed, drilling begins on the well's horizontal section, called the lateral. The pipe used to drill the well measures 30 feet in length and weighs approximately 495 pounds each. It takes over 350 pieces of pipe weighing nearly 87 tons to drill a 10,500-foot well. At various stages of drilling, the pipe is taken out of the hole for tool and bit changes and put back in. This process is called tripping pipe. When the targeted distance is reached, the drill pipe and bit are removed from the wellbore one last time. Production casing is now inserted into the full length of the wellbore. Cement is again pumped down the casing and out through the hole in the casing shoe, forcing the cement up between the casing and the wall of the hole, filling the open space known as the annulus. Casing the well is a very important process because it permanently secures the wellbore and it prevents hydrocarbons and other fluids from seeping out into the formation as they are brought to the surface. At this point, the drilling rig is no longer needed. A temporary wellhead is installed and the location is prepared for the service crew who will perf, frack, and prepare the well for production. The first of these steps is to perf or perforate the casing. A perforating gun is lowered by wire line into the casing to the targeted section of the horizontal leg. An electrical current is sent down the wire line to the perf gun and sets off a charge that shoots small holes through the casing and cement, and out a short distance into the shale formation. The perf gun is then pulled out of the hole. Next, because the shale is tight or compressed, the well will have to be fracked. Known as hydraulic fracturing, this is a process where water, sand, and chemicals are pumped into the wellbore and down the casing under extremely high pressure. As the mixture is forced out through the perforations and into the surrounding rock, the pressure causes the shale to fracture. This creates a fairway connecting the reservoir to the well and allows the released gas to flow to the wellbore. Next, a temporary plug is placed at the heel or left side of the first stage frac. The plug closes off or isolates the perforated and frac section of the wellbore so that the second stage section of the horizontal leg can be perforated and fracked. This process of perfing and fracking can be repeated several times to cover the entire horizontal distance of the wellbore. Once fracking is completed, the plugs are drilled out, allowing the gas to flow up the wellbore. The next step is to install a permanent wellhead, also known as a Christmas tree, and other necessary surface equipment. A pipeline is then built to transport the gas to the pipeline network. As field development expands, additional pipeline infrastructure is built. Thanks to the vision and persistence of those who have perfected these new technologies, shale plays across the U.S. have become an innovative and highly productive source of new energy for our country.
How does the deep-sea drilling vessel Chiku drill into the seafloor? When the vessel arrives at the drilling site, it receives a satellite signal that helps the vessel move into the exact position required. The vessel has 6 propellers that rotate a full 360 degrees and keep the vessel in one position, preventing it from drifting due to the wind, waves, or sea current. First, the conductor pipe is installed. As the drill pipes are connected, the conductor pipe and guide are run down to the seafloor. After the conductor pipe penetrates the seafloor, the drill pipe is released and pulled back to the vessel. A large drill bit connected to the bottom of the drill pipe is run down to the seafloor. The drill bit is led down to the bottom of the hole through the conductor pipe. The drill bit rotates and drills the sediment and rock below the seabed. Seawater is sprayed from nozzles on the drill bit to raise the cuttings to the seafloor. After drilling several hundred meters, the drill bit is pulled back to the vessel. A casing pipe, about 50 centimeters in diameter, is set into the drilled hole to keep it from collapsing. The casing pipe is run down through the conductor pipe and is inserted into the hole using the drill pipe. Cement is pumped into the space between the hole and the casing pipe to fix the pipe in place. After cementing, the drill pipe is released and pulled back to the vessel. The Chikyu is equipped with the riser system in order to drill into the earth even deeper. As the riser pipes are added one after another, the blowout preventer is run down to the seafloor. The blowout preventer is connected to a wellhead which is located on top of the casing pipe. The vessel is now connected to the seafloor via the riser pipe. A drill bit, smaller than the one first used, is run down through the riser pipe and casing pipe. The drilling begins. Once the riser pipe has been connected, drilling mud is used instead of seawater. When the target depth is reached, the drill bit is pulled back to the vessel. To drill the hole even deeper, a narrower casing pipe is set in to protect the drilled hole. After the casing pipe has been installed, cement is pumped into the space between the hole and the casing pipe to fix the pipe in place. Again, an even smaller drill bit is run down through the riser pipe and casing pipe, and the drilling continues. Repeating this process, the Chikyu will drill through the ocean crust to collect fresh, live mantle. This is something that has never been done before. Rotary drilling is used for ocean drilling. Let's look at the features of this method. First, the drill pipes are connected one after another as they run down to the seafloor. The work of connecting the drill pipes and drilling the hole are powered by a motor on the derrick. The drill pipe has a drill bit attached to the bottom. With rotary drilling, the drill pipe is rotated and the drill bit at the end crushes sediment and rock to make the hole. After a while, cuttings accumulate at the bottom and drilling cannot go any further. Seawater or other liquid is then pumped from the vessel down through the drill pipe and is jetted out of the nozzles on the drill bit. This liquid current forces the cuttings up to the seafloor. That is rotary drilling. The deep-sea drilling vessel Chikyu can drill over 7 kilometers below the seafloor into the earth. To drill even further below the seafloor, a riser system is used. With the riser system, mud is used instead of seawater. There are several reasons for using mud. First, it has greater viscosity than seawater to force cuttings up from the bottom of a deeper hole. Also, with the increase in pressure at greater depths, the formation pressure becomes much greater than the pressure in the hole filled with seawater. The hole will collapse if a certain differential pressure between the outside and the inside of the hole is reached. Mud has a higher density than water, therefore the pressure inside the hole remains higher, and the hole will not cave in, allowing deeper drilling. The drilling mud is artificially conditioned with various kinds of products, and it is expensive. Discharging it on the seafloor is bad both environmentally and economically. The mud is therefore collected and reused. For this purpose, the riser pipe is connected all the way from the vessel to the seafloor. The drilling mud sprayed out of the drill bit returns to the vessel through the riser pipe together with the cuttings and is collected and recycled at the vessel. Riser drilling not only makes it possible to drill deep into the earth, it is a breakthrough drilling method that is both environmentally and economically sound. Riser drilling will make it possible to drill all the way down into the Earth's mantle, a depth never before reached in all of history.
There are 5 steps described in these videos. You have planning, drilling, completion, production, and abandonment. A hole 5 to 36 inches in diameter is drilled in the ground. This is called a borehole. After the hole is drilled, sections of steel pipe called casing, slightly smaller in diameter than the borehole, are placed in the hole. Cement may be placed between the outside of the casing and the borehole. Drilling fluids are used to speed up the drilling process. Let us review some of these steps in detail. Drilling can be either developmental, exploratory, or directional. Drilling for unproven reserves is called exploratory drilling. In the past, exploratory drilling were generally known as wildcat drilling. This process was not based on quantitative measurements, such as seismic data. In other words, there was a time in the past when exploratory drilling was based on simply the process of following surface signs, for example, seeps, creek beds, and salt domes, and drilling where the party chief poked his stick. Investors in such wildcat endeavors will reap significant rewards if such drilling results in locating large energy reservoirs. Conversely, wildcat drilling that results in dry holes will lead to adverse performance. Those days are long gone. Petroleum seismology, described in the previous lectures, has revolutionized the search for hydrocarbons and has led to many remarkable discoveries. Drilling in an area with proven oil reserves is called developmental drilling. The developmental drilling is generally used to increase production. For example, many new wells were developed to increase the production of Prudhoe Bay, Alaska, the largest oil field ever found in North America. The Dawing oil field in China, discovered in 1961, has sustained oil production above 1 million barrels a day for over 35 years, thanks to developmental drilling. Since the field is onshore and the wells are inexpensive to drill, this steady production was maintained by constantly drilling more and more infill development wells at increasingly tighter intervals. Dawing's production has significantly declined since 2008. Directional drilling, or slant drilling, also known as horizontal drilling, is the practice of drilling non-vertical wells. Generally, directional drilling involves drilling vertically to a known reservoir, then veering the drill bit at an angle to access additional resources. Directional drilling increases the exposed section length through the reservoir by drilling at an angle. As you can see in this photo here, you have various examples of directional drilling. There in the black is the oil. Aramco re-drilled Ghawar oil field with horizontal wells to increase production. Directional drilling allows us to drill into the reservoir where vertical access is difficult or not possible. For instance, an oil field under a town. Actually, accusations of directional drilling led to the first Gulf War in 1991. Iraq accused Kuwait of using directional drilling techniques to extract oil from Iraqi oil reservoirs near the Kuwaiti border. Iraq subsequently invaded Kuwait. After the war, the border between Iraq and Kuwait was redrawn, with the reservoirs awarded to Kuwait. Most modern wells use an air rotary drilling rig. This is a machine that creates holes in the ground that can operate 24 hours a day. With this process, engines power a drill bit, like the one shown here, a cutting tool used to create a circular hole. The drill bits used in air rotary drilling rigs are hollow steel, with tungsten rods used to cut the rock. Petroleum drill bits are 36 centimeters in diameter on average. As the drill bit rotates and cuts through the earth, small pieces of rock are chipped off. A powerful flow of air is pumped down the center of the hollow drill and comes out through the bottom of the drill bit. The air then rushes back toward the surface, carrying with it tiny chunks of rocks. Geologists on site can study these pieces of pulverized rock to determine the rock strata the drill has encountered. When the drill hits oil, some of the oil naturally rises from the ground, moving from an area of high pressure to one of the low pressure areas. This immediate release of oil can be a gusher, shooting dozens of meters into the air, one of the most dramatic extraction activities. It is also one of the most dangerous, and so a piece of equipment called a blowout preventer redistributes pressure to stop such a gusher. Let us talk about drilling fluids and drilling rigs to conclude this section on drilling. Drilling fluid, often called drilling mud, is used to aid the drilling of boreholes into the earth. The main functions of drilling fluids include preventing formation fluids from entering into the wellbore, avoiding formation damage, limiting corrosion, keeping the drill bit cool and clean during drilling, carrying out drill cuttings, and suspending the drill cuttings while drilling is paused, and when the drilling assembly is brought in and out of the hole. During drilling, cuttings are created, but they do not usually pose a problem until drilling stops because a drilling requires replacement. Again, drill bits require replacement. When this happens and drilling fluids are not used, the cuttings then fill the hole again. Drilling fluids are used as a suspension tool to keep this from happening. The viscosity of the drilling fluid increases when movement decreases, allowing the fluid to have a liquid consistency when drilling is occurring, and then turn into a more solid substance when drilling has stopped. Cuttings are then suspended in the well until the drill is again inserted. This gel-like substance then transforms again into a liquid when drilling starts back up. Another important function of drilling fluids is rock stabilization. Special additives are used to ensure that the drilling fluid is not absorbed by the rock formation in the well, and that the pores of the rock formation are not clogged. Drilling fluids are compressed air, water, oil, or synthetic based, and each composition provides different solutions in the well. Oil-based drilling fluids may work better with a saltier rock. Water-based drilling fluids are generally considered to affect the environment less during offshore drilling. Disposal of drilling fluids after they are used can also be a challenge. Methods for recycling drilling fluids are being used. Let us talk about drilling rigs to close this section on drilling. On land, oil can be drilled with an apparatus called an oil rig or drilling rig. Offshore, oil is drilled from an oil platform. Drilling offshore is much more expensive than drilling onshore. It usually uses the same drilling techniques as onshore, but requires a massive structure that can sustain the tremendous strength of ocean waves in stormy seas. Offshore drilling platforms are some of the largest man-made structures in the world. They often include housing accommodations for people who work on the platform, as well as docking facilities and a helicopter landing pad to transport workers. The platform can be tethered to the ocean floor and floated, or a rigid structure can be used that is fixed to the bottom of the ocean, the sea, or a lake with concrete or steel legs. The Hibernia platform, which is 315 kilometers off of Canada's eastern shore in the North Atlantic Ocean, is one of the world's largest oil platforms. More than 70 people work on the platform in 3-week shifts. The platform is 111 meters tall and is anchored to the ocean floor. About 450,000 tons of solid ballast were added to give it additional stability. The platform can store up to 1.3 million barrels of oil. In total, Hibernia weighs 1.2 million tons. However, the platform is still vulnerable to the crushing weight and strength of icebergs. Its serrated and sharp edges can withstand the impact of sea ice or icebergs. Now let's talk about completion and production. The oil production starts by drilling a hole 14 centimeters to 80 centimeters in diameter in the ground. Once a well has been drilled, the decision must be made to either turn it to a producer well or be plugged and abandoned if it is dry, if the amount of oil in place is not economically viable, or if the potential recovery factor is just too small. If the decision is to develop the well, completion operations must be undertaken. Well completion involves a set of steps needed to transform a drilled well into a producing well. As we pointed out earlier, these steps include casing, cementing, perforating, and installing a production tree. Let us briefly describe each of these steps. Casing is the first step in completing a well. Casing consists of a steel pipe that is joined to make a continuous hollow tube, which is run into the well. Without the casing, the well would eventually close in upon itself after the drilling fluids are withdrawn from the well. Moreover, the casing prevents contamination of freshwater zones. Cementing is the second step. Cementing the well consists of pumping cement slurry into it to displace the existing drilling fluids and fill in the space between the casing and the sides of the drilled well. Perforation. In order to have production, the casing and cement are perforated to allow the hydrocarbons to enter the well stream. This process involves running a perforation gun into the wellbore. The gun then shoots holes in the sides of the well at a defined location, allowing the hydrocarbons to enter the well stream. Gravel packing prevents sand from entering the well stream. More complicated than cementing a well, gravel packing requires a slurry of appropriately sized pieces of coarse sand or gravel to be pumped into the well before the slotted liner of the casing and the sides of the wellbore. The wire screens of the liner and the gravel pack work together to filter out the sand that might have otherwise entered the well stream along with the hydrocarbons. Production tree. On the last step of well completion, the workover rigs used to drill and complete the well are moved off the wellbore, and the top is outfitted with a collection of valves called a Christmas tree or production tree. In summary, completion are small holes or perforations made in the portion of the casing which passes through the production zone to provide a path for the oil to flow from the reservoir into the production tubing. In the production stage, the oil and gas are produced. The workover rigs used to drill and complete the well are moved off the wellbore, and the top is outfitted with a collection of valves called a Christmas tree or production tree. Abandonment. A well is said to reach an economic limit when its production rate doesn't cover the expenses. Let's discuss the actual oil production. In primary oil recovery, big oil wells initially flow spontaneously. Oil comes to the surface because the pressure of a column of natural gas and oil inside the pipe is less than the pressure inside of the reservoir rock. As production continues, the reservoir pressure falls, and the nodding pump jacks are used to lift the oil to the surface. Primary production extracts less than a quarter of the original oil. A pump jack is the overground drive for a reciprocating piston pump in an oil well. A pump jack is used to mechanically lift liquid out of the well if not enough bottom hole pressure exists for the liquid to flow all the way to the surface. The arrangement is commonly used for onshore wells producing little oil. Pump jacks are common in oil-rich areas, for example, West Texas. In early oil field practice, primary production continued until wells in a field produced too little to cover the production costs. It was then time to institute secondary recovery. This commonly involved pumping water under very high pressure into some of the wells and extracting oil from others. This process, called a water flood, and is the most common secondary oil recovery method. As you can see in this picture, primary production produced 5 to 25% oil, and in secondary production, you got 5 to 15% production. How the water flow works. The water flooding is a void replacement process. Injection of water brings the reservoir pressure to its initial level and maintain it near that pressure. The water displaces oil from the pore spaces, but the efficiency of such displacement depends on many factors, for example, oil viscosity and rock characteristics. In these pictures you see here, in the first one, you have a microscopic view of oil and sand compacted under pressure in the oil reservoir. After primary production, oil still remains in the reservoir, but is increasingly difficult to recover. As the water flood continues for some time, eventually the water finds the path of least resistance through the reservoir. Open up in the oil-bearing rock. Some of the injected water is circuited directly to the production well without pushing much oil out of the rock. At some point, the majority of the injected water is circuited directly to the production well without pushing much oil out of the rock. Oil production falls dramatically. We end up producing essentially water instead of oil. Many oil fields are shut down due to high operating costs and little return. In other cases, tertiary recovery is activated. Modern practice starts the water flood early, sometimes simultaneously with initial production. Another secondary recovery method today is gas drive. During this process, a well is intentionally drilled deeper than the oil reserve. The deeper well hits a natural gas reservoir, and the high-pressure gas rises, forcing the oil out of its reservoir. Let me repeat this. Another secondary recovery method today is gas drive. During this process, a well is intentionally drilled deeper than the oil reservoir. The deeper well hits a natural gas reservoir, and the high-pressure gas rises, forcing the oil out of its reservoir. The next part we will discuss is tertiary oil recovery, which involves using principles of enhanced oil recovery, such as the injection of carbon dioxide. Carbon dioxide is soluble in water, but it is even more soluble in crude oil. The carbon dioxide bulks up the oil droplets, and they start to move again, After the oil comes to the surface, the carbon dioxide is stripped off and sent back downstairs to hunt for more oil. Let us now turn to the methods for producing unconventional oil and gas. With the dwindling of conventional oil resources, the exploration and production industry is turning more and more to unconventional oil resources, namely heavy oil, tar sand, also known as oil sand, and oil shale, as we discussed in the previous classes. These oil resources are characterized as unconventional because they do not flow like conventional oils. In some cases, they do not flow at all. Moreover, methods of exploration and production, even of the refining of these oils, are different from those of conventional oils. Before we turn to our objective of describing the two key technologies behind unconventional oil and gas recoveries, namely hydraulic fracturing and thermal recovery, let us point out why the amount of unconventional oil and gas, especially shale gas, may turn out to be larger than the amount of conventional oil and gas. Shale, sandstone, and carbonates make up about 99% of all the sedimentary rocks, with shale being the most abundant and carbonate the least abundant. Conventional oil is sandstone and carbonate. Unconventional oil consists of shale. Shale are more abundant than sandstone and carbonate combined. Therefore, the likelihood of shale gas is greater than that of conventional oil and gas. As described in a previous lecture, migrations of conventional oil and gas are halted by impermeable rocks known as sills or cap rocks. Shale is one such rock, therefore it is impermeable. Shale is also a reservoir because it contains gas in some basins. So we have to artificially stimulate the permeability of shale, or frack the shale, in order to recover unconventional gas. That is what hydraulic fracturing is about. Hydraulic fracturing consists of injecting large volumes of water, also known as pad, at a higher pressure than in situ stress into tight reservoirs to induce increases in the reservoir permeability by causing the rock containing gas to crack or fracture. This pressure-induced permeability is maintained in the reservoir by injecting macro-sized particles called propanes when the pressure is released. Fractures compress onto propanes, creating high permeability pathways which allow oil and/or natural gas to flow back into the well and to the surface. In the Barnett Formation, a typical fracture in a horizontal well will involve 3 to 4 million gallons of water and 1 million pounds of propane per fracture stage. And there can be as many as 20 stages along a single horizontal run. In addition to injection of high pressure in water and propane to produce and propagate hydraulic fractures, the production of shale gas requires drilling horizontally through the shale formation and fracking the shale to artificially induce permeability. The key steps are 1. Drilling horizontal wells through the formation. 2. Installation of a cement casing. 3. Perforation. 4. Injection of high pressure in water and propane to reduce and propagate hydraulic fractures. Let me repeat this. In addition to injection of high pressure in water and propane to produce and propagate hydraulic fractures, the production of shale gas requires drilling horizontally through the shale formation and fracking the shale to artificially induce permeability. The key steps are 1. Drilling horizontal wells through the formation. 2. Installation of a cement casing. 3. Perforation. And injection of high pressure in water and propane to produce and propagate hydraulic fractures. Operators typically pump in stages, using from 2 to 4 perforation clusters for every 150 meters of lateral section. The problem is, with a 600-meter lateral extend and only 4 stages, there are just 8 to 16 zones of entry. That leaves almost 90% of the rock untouched. Ideally, the best scenario would be to pump 40 or 50 smaller stages, putting the fractures as close together as possible. But that is not practical and is far too expensive with current technology. As hydraulic fractures propagate, swarms of microearthquakes, which are harmless, are generated locally. The 3D map of these induced microearthquakes or microseismic events can be recorded by sensors located on the ground surface and can then be used to infer the spatial extent and location of the fracture network zone. Microseismic fracture mapping can also be used to improve the evaluation of hydraulic fracturing in horizontal wells by locating regions which are more permeable in the shale and therefore more suitable for hydraulic fracturing. This figure shows a microseismic data acquisition. Data are recorded by sensors either distributed at the surface or in a dedicated borehole. This acquisition is considered passive because it does not involve typical seismic sources, such as fibrocide and dynamite. Thermal oil recovery is a recovery of oil that does not flow readily or that does not flow at all. The objective of thermal oil recovery is to reduce oil viscosity in order to facilitate its displacement. Let me repeat that. The objective of thermal oil recovery is to reduce oil viscosity in order to facilitate its displacement. The common methods of thermal oil recovery are steam-assisted gravity drainage and cyclic steam stimulation. Cyclic steam stimulation uses high-pressure steam injected by a vertical well, soaking the oil sands and softening the tar-like bitumen, and then pumping it to the surface using the same well bore. To ensure success, the process has to be cyclical. The well is put through cycles of steam injection, soaking, and oil production. First, steam is injected into a well at a temperature of 300 degrees Celsius for a period of several weeks or months. The well sits for several days to let heat enter the oil sands. The hot bitumen is then pumped, sometimes taking weeks. When the production rate falls, the well is put through several more cycles of injection, soaking, and production until the cost of injecting steam exceeds production costs. This method began to be commercially used in 1985 by Imperial Oil at Cold Lake. Steam-assisted gravity drainage thermal recovery combines horizontal drilling with thermal steam injection. A pair of wells is drilled into the ground about 5 meters apart, and steam is injected into the reservoir through the top well. The steam softens the tar-like bitumen and enables it to flow out of the reservoir and into the lower well. From there, it is pumped to the surface. Cyclic steam stimulation uses high-pressure steam injected in a vertical well to soften the tar-like bitumen and then pumped to the surface using the same well bore. SAGD thermal recovery combines horizontal drilling with thermal steam injection. A pair of wells are drilled about 5 meters apart and steam is injected into the reservoir through the top well. The steam softens the tar-like bitumen and enables it to flow out of the reservoir and into the lower well. From there, it's pumped to the surface. Now it's time for a small quiz. The question is heavy oil recovery carried by hydraulic fracturing? Now we're back. The question for the quiz was, is heavy oil recovery carried by hydraulic fracturing? The answer is no. Heavy oil recovery is about decreasing the viscosity of oil so that it can flow into the production well. Let's discuss reservoir monitoring, including permanent monitoring reservoir. Seismic surveys acquired at different stages in the life of an oil or gas reservoir can provide time-lapse snapshots of the fluid distribution over production time. This technique, called four-dimensional or 4D seismic reservoir monitoring, is helping the exploration and production industry delineate bypassed hydrocarbons and design development drilling programs to optimize recovery and extend the life of some petroleum fields. Here's an illustration of seismic data acquisitions. The second illustration is of seismic imaging results. And the third illustration is a structure and fluid content derived from seismic imaging results. This figure shows results of two seismic surveys, 1985 and 1999. The 1999 survey, at the bottom, clearly shows the effect of production when compared with the baseline survey of 1985, which is at the top. The change in the seismic reflection strength of the top of the reservoir is related not only to the saturation change, but also to the original oil column height. When water replaces oil, a dimming effect is observed on what used to be a strong response from the top of the reservoir. The strong seismic response from the oil-water contact in 1985 has also been dimmed in 1999 due to production. Red and yellow colors represent a decrease in acoustic impedance, while blue colors represent an increase in acoustic impedance. Structure and fluid content are shown in the cross-sectional models on the right. On the left of the fault, we can see that almost all oil accumulation has been drained by 1999, whereas much oil is still to be recovered from the main accumulation on the right of the fault. So 4D seismics allow the oil and gas industry to extend the profitable life and effective production of existing reservoirs, and to make small and complex fields economically viable. Extending the life of existing reservoirs is as important as finding new oil fields, even more important than new oil fields in some cases. Time-lapse seismics are also used to monitor the injection of carbon dioxide, or CO2, into deep subsurface rock formations for long-term storage. The capture and injection of CO2 produced by human activities are part of a portfolio of options that can reduce CO2 emissions into the atmosphere and help to mitigate climate change. The classic example is the Sleipnir CO2 injection site, where CO2 has been injected since 1996 into the saline aquifer Otsira FM, 1,000 meters below the sea surface. The Otsira FM is a sequence of clean high-porosity sandstones, which in the Sleipnir area is 200 to 300 meters thick. By the end of 2013, about 15 megatons of CO2 had been injected. In 1994, prior to the injection start, a base seismic survey was acquired, and 8 repeated seismic surveys have been acquired and compared to this baseline in 1999, 2001, 2002, 2004, 2006, 2008, 2010, and 2013. This figure shows seismic displays of the development of CO2 inside a layer with time. The large contrast in elastic properties, in particular P-wave velocity, between water-bearing sandstones and CO2 gas-bearing sandstones make the monitoring quite simple. These figures show seismic images of the development with time of injected CO2 at the Sleipnir CO2 injection site. So time-lapse seismic expertise can be used to monitor and analyze the behavior of a subsurface CO2 repository, like that at the Statoil-operated Sleipnir field. Now let's talk about permanent reservoir monitoring. Permanent reservoir monitoring, or PRM technology, involves permanently embedding the nodes or streamers into the seabed. Once a seafloor recording system is in place, it is a straightforward and relatively inexpensive option to collect seismic data. A ship with a signal source will cross the field, and the nodes or cables on the seabed will register the signals and transmit them to the platform and onshore for data processing and interpretation. The concept of seabed multi-component time-lapse, or 4C4D seismic permanent reservoir monitoring, is attractive for oil production because it can provide frequent images of the reservoir. These images impact the improved oil recovery programs. Aspects of improved oil recovery that permanent reservoir monitoring impacts include well placement, completion, fracture monitoring from active and passive microseismicity, and floodfront monitoring. Typical towed streamer repeat surveys occur on a timescale of 2 to 5 years. By contrast, nowadays, the time between PRM surveys varies from 3 to 9 months. In other words, the timing of monitoring surveys is now more flexible, and the time intervals between monitoring surveys are getting smaller. The smaller time intervals between monitoring surveys are needed to assist in reservoir management decisions, which are today made on a timescale of weeks or months rather than years. Let me repeat this. The smaller time intervals between monitoring surveys are needed to assist in reservoir management decisions, which are today made on a timescale of weeks or months rather than years. Moreover, the cost of permanent reservoir monitoring surveys is much lower than the initial cost of installation, which is still a major problem. Also, permanent seismic receiver arrays open up new opportunities for extra information gathering in the form of passive seismic monitoring between monitoring surveys. The increasing amount of data produced by these permanent reservoir monitoring systems increases the value of current developments in advanced processing and interpretation methods. Thank you for listening to this iMode Education lecture. Remember, there are multiple exercises at the end of this lecture that advise you to study. Also remember that there is a large selection of iMode Education lectures which can further enhance your knowledge of energy.